Okay, provide a multi-step synthesis for the following transformation of this alkene to alpha beta unsaturated and substituted cyclohexanone. Okay, so as you can see, you have a ketone here, and to the alpha and the beta position there is substitution, and there is also a carbon-carbon double bond here, unsaturation. Okay, so which means this obviously involves the enolate chemistry. That means you first have to get the cyclohexanone and then generate the enolate, and then put substitutions on the alpha and the beta positions, and then finally generate a double bond in the alpha and the beta positions as well. Okay, so let's first see how you can get a cyclohexanone from cyclohexene. So simply add acid and water and heat, which is going to hydrate the carbon-carbon double bond, and you are going to get cyclohexanol. And use any oxidizing agent, Jones reagent, PCC, Swern oxidation, DMP, all those things will work. Okay, so oxidize that to get the cyclohexanone in the molecule. Now once you get your cyclohexanone, now you should introduce the alpha carbon chemistry here, so that you can put substitutions on the alpha and beta positions. So if you want to put substitutions on the alpha and beta, you should first get your alkene. So what you're going to do is add bromine, Br2, and heat, and acid. Okay, that is going to give you the bromine on that position. Now if you treat that with the base like sodium hydride, it is going to give you an elimination product, and you will get the alpha beta unsaturated cyclohexanone, alpha beta unsaturated cyclohexanone, which is the cyclohexenone. And now if you have a conjugated carbonyl like this, you can use your conjugated addition, which is Michael addition, to be able to get a substitution on that carbon. So this is where you will use your Gilman reagent, and since we have ethyl groups here, it is going to involve dialkyl or diethyl cuprate, right? And this will give you conjugate addition, and you will end up getting substitution on or addition on that fourth position, and you're going to get the enolate that looks like this, because it is going to be conjugated to give a resonance form that looks like that. So this is the enolate, and don't treat this with acid water, because if you treat it with acid water, you'll get the ketone. But then again, if you want to introduce a substitution on the alpha position, you will have to deprotonate the carbon again. So instead of doing all that, you can just not treat it with an acid, keep this as an enolate, and now react this with ethyl iodide, because you will have a substitution reaction on the alpha position now. So this is going to give you alpha beta diethyl cyclohexanone, and if you do the same chemistry that you did in the first step, you're going to again introduce your bromine on the alpha position, and bromine is going to go to this position as opposed to the other side, because the enol you produce is going to be the more substituted enol, which is going to be the more stable and the major product when you convert this to the enol form with the acid. Okay, so the reaction happens on the same side again, and again if you treat this with a base like sodium hydride, again you're going to get a double bond back on the same carbon-carbon position. So that's how you will do your multi-step synthesis.